If you've ever seen an aurora, you know that they are truly incredible. These colorful displays of light take place in Earth's upper atmosphere and can stretch for hundreds of kilometers. But while we're pretty familiar with our own aurora, it turns out that other planets' aurora could be way crazier. And I mean way crazier, like maybe even scarier. Like, did you know that one planet's aurora may switch places twice a year? And don't worry, we'll explain why that's possible. And then at the end, we'll tell you about this planet's terrifying secret. Aurora form when charged particles from space, like those found in solar wind, interact with a planet's atmosphere. Our aurora appear at Earth's North Pole and South Pole, but not all planets have their aurora there. Uranus is a prime example. You see, a planet's aurora tend to line up with its magnetic poles. And that makes sense because planetary magnetic fields tend to form from the movement of a planet's metallic deep interiors. And since Earth's magnetic field is generated by our rotating iron-rich core, our magnetic North Pole is very close to our geographic North Pole and our magnetic South Pole is close to our South Pole. That means when the solar wind hits these areas of the planet, it creates aurora. But here's where things get weird. While Earth's poles are fairly close to the rotational poles, Uranus's magnetic poles aren't. In fact, they're tilted 60 degrees away from the planet's rotational axis. And that has some pretty major implications for its aurora. You see, Uranus rotates on its side. Scientists think something huge has crashed into the planet in the past, which could explain why it rotates so oddly. And while that probably didn't feel good for Uranus, it does make for some pretty interesting aurora. Since the magnetic poles are so far from the rotational poles, the magnetic poles are actually above Uranus's equator for half of the year. That means that half of the year, the aurora appear at Uranus's equator. But then, as Uranus rotates, the magnetic poles move away from the equator, and by the end of the year, they're at the opposite end of the planet, circling Uranus at its North Pole. So in just one Uranian year, its aurora go from the South Pole to the North Pole to the equator back to the South Pole. And if that seems confusing, it's because it is. Trying to keep track of what's going on with Uranus' magnetic poles can be really hard. So let's break it down. As we said before, Uranus rotates on its side, relative to the Sun. One side of the planet faces the Sun for almost exactly half of each year, while the other side remains in darkness for the same amount of time. The side that faces the Sun experiences summer for 21 years and winter for 21 years. And the opposite side goes through the same thing, just at the same time. So basically, if you want to visit the aurora at Uranus's South Pole, you better bring a really good jacket, no matter what time of year it is. The reason for this super long season is that Uranus is on its side. Its axis is so far from perpendicular to the Sun that it gets way more intense sunlight during half of each year than the other half. And as it rotates, different parts of the planet face the Sun for longer or shorter periods of time. But again, because Uranus rotates on its side, there are two hemispheres that experience extreme seasons at the same time. So when the magnetic poles are located around the equator, the northern hemisphere is experiencing summer and the southern hemisphere is experiencing winter. Since the magnetic poles are now closer to the equator, the aurora that formed there are closer to the summer solstice, when the northern hemisphere receives the most direct sunlight. For Earth, this occurs on June 21st. At this point, Uranus's magnetic poles are tilted 30 degrees relative to the Sun. But as Uranus continues rotating, the magnetic poles move away from the equator and closer to the North Pole. As they do, the northern hemisphere moves into winter and the southern hemisphere moves into summer. This also means that the magnetic poles are now closer to the South Pole, and the aurora will begin to gather there. By the end of the year, the magnetic poles are once again tilted 30 degrees relative to the Sun, but now they're pointed away from it. So the aurora circling Uranus's North Pole are now lit up by the Sun's reflected light. To sum up, every 6 days or so, Uranus's Aurora switch locations. This means that the magnetic poles must move faster than Earth's. pulls by a factor of 16. Because a year on Uranus is 16 times longer than a year on Earth, these aurora switches happen only twice a year. And although we know the aurora switch locations twice a year, we're still trying to figure out how they get there. You see, the aurora don't just appear out of nowhere. They recreated by chemical reactions between gases in Uranus's atmosphere and the charged particles from the solar wind. The most common gas on Uranus is hydrogen, but it's not the only one. Uranus's atmosphere is also mostly made up of helium and methane, and those two elements play a key role in creating aurora on many planets, including our own. That's because these molecules absorb energy from the charged particles in the solar wind and then release that energy as light. But scientists are still working on figuring out exactly how the energy transfer works for Uranus. And part of the problem is that getting close enough to the planet to observe its aurora is really hard. Even NASA's Voyager probes, which flew by Uranus in the 1980s, couldn't get close enough to see Uranus's aurora. The European Space Agency's ESA, 14-year-long, Voyager mission was able to get within 8,500 kilometers of Uranus. But that's still 17 times farther than the Voyager probes were from the planet when they took their famous pictures of the pale blue dot. That's because Uranus doesn't have much of an atmosphere to slow the spacecraft down as they approach the planet. And without a thick atmosphere, there isn't much atmospheric drag either. So the ESA probe was able to maintain a speed of 135,000 kilometers per hour as it passed right by Uranus. Now, that's fast, but it was still too quick to see Uranus's aurora. To pull that off, you would need to fly even closer than the Voyagers. And the only spacecraft ever to come close enough was NASA's Cassini probe. But that was only after it had already visited Saturn. So studying Uranus's aurora remains a challenge, but scientists are up to the task. In the near future, we hope to learn more about how Uranus's aurora form and whether or not they are as big as the ones on Earth. And if you think that's exciting, stick around until next week, because we're going to talk about one of Uranus's terrifying secrets. Thanks for watching. If you liked this video, press the like button to stay up to date with all our future videos.